So, good afternoon, everyone. My name is Annajiro challa. So, I'm a master student at State University of New York at Binghamton. So, today I'll just talk about the effect of noise on the density classification task for various cellular automata rules. Previously, our title is Investigating the Effect, but right now we already did the investigation and we had some results. So I know most of the majority of the folks already know what is cellular automata, but just a quick introduction. So cellular automata are discrete dynamical systems and computational models that consist of a grid of cells. And these cells have some finite number of states, and these states change based on some rules that are applied onto them. So as you can see, we have a lookup table for rule 30 on the left. So based on some input neighboring combinations, we're able to get some outputs, which we're calling them as rules. So this is for a neighborhood of 3. And you could see a cellular lattice on the right side, like a state space diagram. So generally, in reality, this grid is not truly a grid. Like it's like a toroidal shape. And next, I'll introduce about density classification task. But before we go in there, let us look at this code for a second. So consensus emerges through interaction. So imagine if we have 5 students in a room, and initially each person have different ideas. But after 1 hour, maybe they can all collaborate on a single idea and formulate a research paper. So how, if they're interacting with each other, how their unique ideas were merging to a single idea? That is the basis of the density classification task. So the density classification task also has a huge relation with the biological processes, like more like a quorum sensing or quorum signaling processes. So it's a computation problem, and the objective is to establish some rules where the automata converts to a uniformly majority state. So if, let us say here we have a state space diagram on the left with a neighborhood of 7. And as you can see, on the right, we have a zoomed in view of the left lattice. And at the initial time step, if the majority is 1, at the final time step or at a defined time step, the majority is again 1. So the objective is this. The objective is to make sure the initial majority always matches with the final majority. And this is generally not an easy task because if you look at the quorum sensing, whenever the bacteria or the microbial organisms are kind of having some interaction, their global phenomenon or their behavior keeps on changing. So in the biology or in the biological processes, like any bioluminescence kind of things, uh, this majority classification task is very high to very difficult to achieve because they interact and they have to uniform at a point. But what we are doing is we are not just trying to measure the performance of the rules on the density classification task. We're also trying to introduce some kind of noise, and we would like to see whether the rules are still able to maintain that kind of interaction or not. So these are the rules that are covered, and as you can see, these are the top 13 high-performing rules. And on the right, we have their accuracies. The performance for 100,000 samples and 149 lattice. And by the way, like achieving 100% accuracy is not possible. So these rules, irrespective of their random initial conditions, they're trying to come to a uniform state. So that is their accuracy for 100,000 samples, and we measured it. And here is my research question. It's pretty straightforward. How do the CA rules perform on the DCT when the noise is introduced? So, for example, if there is a CA rule, and generally without noise, as we have already seen their accuracy. So with noise, how their accuracy keeps on changing. And the rules that we are using are having a neighborhood of 7. So totally we have 128 bits in their binary representation. And the type of noise we are using is stochastic noise. So as you see on the right side, we have a cellular lattice with some red colored cells. So this is how the noise is being introduced. So it will be introduced at a random time step at a random lattice position. And this perturbation can basically make the cellular automata lose its local information over the time, or sometimes it can leave it without any strong impact. So that's what we would like to measure. And here is a representation of the noise on the cellular lattice. So if you could see, this is the representation of the lattice for GEP1 rule, and the first four samples are having no noise with the way that we introduce noise has a defined probability. And as you see, the first four cells, the probability is zero, and the next four cells have the probability of 0.1, which is 10%. And the lattice was so disturbed that you could see, uh, and out of four instances, there are only one instance that density classification task actually achieved. So as you could see on the top of the lattices, we write correct and incorrect. So correct indicates that lattice has converged to a uniform state, and incorrect indicates that lattice did not converge to a uniform state. With what certain initial conditions has it began with. So this is our design of experiments. We have 13 rules, 3 lattice sizes, mainly 149, 349, 549, and we took 50 noise points between that 0 to 0.1, and with an interval of 0.002. And this entire design computes or produces 195 million simulations. And for this simulations, we had one of our colleague, Dr. Rosa, came with a package. It's a CUDA based package by the name CubeWalkers. So using CubeWalkers, you could just simulate these kind of cellular lattice for a lot of samples or for a bigger simulation like this. So these are some of the results that we got. So here you can see a heat map, and the orange color represents the higher accuracy and the blue color represents the lower accuracy. Let me, yeah. So here on the y-axis, you see we have our 13 rules, right? So these rules were actually sorted based on their accuracy at a noise equal to 0. For example, here at noise equal to 0, we have recorded their accuracies, and by that we just sorted this sorted and represented in that way. And you can see the top performing rules like FWO2, FWO1, which has a tremendous accuracy like 89%, does not show any robustness. They are quickly dropping to an accuracy of 0 if the noise is introduced. And rules like GP, GEP2, they are able to retain that kind of robustness. They're not even, even though the noise is introduced, they are able to show some stable patterns, and their accuracy is, their accuracy is not dropping that much, that faster. And we repeated the experiment for the 3 lattice sizes, and as you can see, as we keep on increasing the lattice size, the accuracy drops even faster. And on the left, as you can see, we have an accuracy versus noise graph for the GKL rule. And here we just mentioned the AUC as area under the curve. This AUC is fundamentally different from machine learning, where we plot it for true positive rate and false positive rate. So here, whenever I say AUC, that is that is the robustness, like the area under that accuracy curve. And we would always want this area to extend exponentially, because we would like to have whenever we increase the noise, we would like to we expect the rules to have that kind of accuracy, and they should be retaining them. And we just plotted on the right, we plotted for the 149 lattice. And as you can see, we have it for the AEC rank is on the y-axis, and the normal performance, like the accuracy at the noise equal to 0 or no noise, is on the x-axis. And with this representation, you could see the top performing rules, again, like FWO1, FWO2 were, and the axis is inverted, by the way. And even though their performance, even though their ranking is at the very top, like 1 and 2, when it comes to the AUC, when it comes to the robustness, they're not that great. So again, we had it for 349 and 549, and you can see there is no big of a difference, but very small and minimal adjustments. And let me introduce another measure of robustness, which is canalization. So again, canalization is highly related to developmental biology. In developmental biology, even though we have different pathways, even though we have different genetic or environmental variations, we might end up with a similar phenotype. So that is how the canalization checks in. And as you can see, we have a lookup table representation on the left. And we are introducing some kind of wildcard schema, which is represented with the pound sign on B. So we are just trying to reduce it or simplify it. And how we are able to simplify it? We are using something called Cohen-McCluskey minimization algorithm. Using this algorithm, we are trying to reduce this lookup table to more like an reduced lookup table or reduced automata. And as you could see, the figure A or the lookup table A has been reduced to B, and from B we just try to swap. So for example, here f-2 and f-3 were swapped and formulated to the representation C. So by doing this, we would be able to see the measure of redundancy, which is input redundancy and input symmetry. Input redundancy helps us identify how redundant the rule input conditions are, and symmetry will able to understand how stable patterns that we could bring up from a rule. So we calculated those measures, and we used a package called CAM, and which is also from our lab. And as you could see, the performance versus, as you could see, we have 4 graphs right here, and we have the comparison versus no noise, and we have the performance versus noise. And you could see rules like GKL, GP, they are having some high redundancy, so that is why they're able to retain that kind of performance or robustness. So this provided us with that evidence that top performing rules can be less robust to noise. So this is for 349, 549. So these are very similar results, but we just repeated for the three lattice sizes. So the conclusion would be we got our answer on how the rules will perform. And one of our colleagues' paper, like Dr. Rocha, my advisor's paper, in his paper, there is an in the conclusion section, there is a hypothesis that he said that top performing rules can be less robust noise. And we found some explicit support to this hypothesis. And in the future, we would like to generate some new rules which are not only having some high performance without noise, but also with noise. So using some genetic algorithm and optimization techniques, we would like to bring up those robust rules. And according to our measures, these are the top 3 performing rules across these lattice sizes. So these are the references that we have used, and any questions?